James Lewis. We're here with Chapter 19 homework. We're going to start with question number 2. Two springs of constants K1 and K2 are connected in series to a block A that vibrates in simple harmonic motion at the period of 5 seconds. When the same two springs are connected in parallel to the same block vibrates at the period of 2 seconds. Determine the ratio K1, K2 of the two spring constants. So first we're going to make our free body diagram. We're going to label them number 1 and number 2, just so that we can keep track of periods and some of the other variables. We have our setup 1 with K1 on top of K2. Our period is 5 seconds. And then our position 2, K1 and K2 are right next to each other in parallel on block A, and T2 is 2 seconds, and the period for 2 is 2 seconds. So the K1, K2, so we got to find our ratio K1 and K2, and our period, and then we have our equations. Our natural period is 2 pi over our natural angular velocity omega, and then we have our angular velocity, our natural angular velocity squared equals k over m. So first off, we start off with our positions. I think I either start off with number 1 or number 2, either way. Anyway, we're gonna start with number 1. So number 1, we have to figure out our our deltas, or the distance that the string stretches in total. So we have a delta 1 and delta 2 based off of which spring we're using. So we'll set up our equation delta equals delta 1 plus delta 2. Our delta converts over to p over k. So we have our delta equals to p over k1 plus p over k2. K is equal to p over delta. So first off, we're just going to make sure to write out all of our equations first, so that we can have all of our resources first. And we're trying to get everything. We're trying to get everything in terms of the single variable. So first off, we're going to go k equals p over delta, and then we have our angular velocity. We have our angular velocity squared equals km. Our angular velocity is equal to the square root of km. Our natural period is equal to 2 pi over natural angular velocity. We're going to insert the natural angular velocity into this equation, which is going to give us 2 pi times the square root of m over k, and then our natural period is then going to be equal to 2 pi, and then we're going to insert in the k value, which is our p over delta, which, since it's over k, we're going to flip that, 2 pi square root of m delta over p, and then we're going to insert in our equation for delta, which I just flopped the 2 pi and the squared over to our period, because we already have the period for our equation, so that's all going to turn into just one constant, one constant. So I just flopped those back over to the left side. Just made it a little easier in the end. So natural period over 2 pi squared equals m times delta divided by p. So then we have our m divided by p times our delta, which is our p over k1 plus p over k2, and then we have all of that equal to m, so that makes all of the p's cancel out, so we have our m over k1 plus m over k2, and then we set that equal, and then we just so that we could get the mass out of the system and onto one side, just did some little algebra there, or arithmetic, whatever that is. I always lose track. So we want to get everything in terms of m, and the reason why, and I was kind of trying to figure this out as I went. The reason why I decided to go with everything's equal to m is because the mass of A is equal in both equations, and that was one of our variables that was equal, and so since it was equal and it isn't given, I might as well cancel that out. So that we don't have to use it. So that's why I made our number 1, our position 1 equation there. Now we're moving on to position 2. We're going to try and get everything equal to m. We have our P equals K1 delta plus K2 delta, and the reason why this one's different than the first equation we can just add everything together, the delta 1 plus delta 2, but in this case the delta, to get P, we have to multiply delta by the individual K constants, and seeing as they're both moving down the same distance, since we're moving down the same distance, we have to separate the K's in that different way since they're in parallel. So we have our K equals P over delta equals K1 plus K2. Our natural angular velocity is equal to square root of K over m. Tn equals 2 pi over W over omega n. Tn equals 2 pi over m divided by K. Same thing as the first position, or as the first setup. We're just going to input our natural angular velocity into the equation, and then we're going to stick in our other values here. For K, let's see, which one did I put in? Oh yeah, it was for K, because K is equal to K1 plus K2. Because this position. Oh, I remember now. In this position, we have both of them. We have a single K constant, because both of them are in parallel, so they're adding together. Whereas this one, we have a single delta constant because the distance comes down the same. The springs don't come down the same distance. K1 doesn't. The spring 1 doesn't come down the same as K2 over here, so we have to separate out by delta. And this one, the springs come down the same. But it's not the same as up there. Anyway, going back, we insert K1 plus K2 for our K constant, and then we have everything equal to mass. Our natural period of the second position over 2 pi squared times K1 plus K2 equals m. So now we'll go ahead and add both of these. Equations together. We're going to have our natural frequency 1 over 2 pi squared. Anyway, I'm going to go through this a little quicker, taking a little while. We have everything equal to each other. 2 pi squares cancel out. And then we have Tn1 squared over Tn2 squared, which is 25 over 4. And then we have that as K1 plus K2 squared over K1 times K2. So now we need to figure out what the different K's are. And the values that we came up with are 1 and 4, because 1 plus 4 squared is 25, and 1 times 4 is 4. So that's how we got that number. And it took me a little while. I was doing a bunch of erasing. You can see some of the marks over here. I was trying to figure out what K1 and K2, how to differentiate between them. But then I realized that it really doesn't matter which one's which, because whether we put K1 on top of K2 in position 1, or K2 on top of K1 position 1, or in position 2, if we put K1 on the right, or K1 on the left, or K2 on the left, or K2 on the right, the periods are going to be the same, the masses are going to be the same, the angular velocity, all of those things are going to be the same. So the only difference here, so there really isn't any difference between the K1 or K2. So they are interchangeable in either equation 1 or 2. So our ratio is going to be 4 to 1 or 1 to 4, however you want to set it up. That is our answer for the first equation, or for question 2. Then we moved on to question 4. I was a little bit confused about question 3, so I decided to move on to this one. We have our single mass, uniform cylinder in the middle. Over here to the computer. A 6 kilogram uniform cylinder can roll without sliding on a horizontal surface and is attached by a pin at point C to the 4 kilogram horizontal bar AB. The bar is attached to 2 springs, each of constant K equals 5 kilonewton meters as shown. Knowing that the bar is moved 12 millimeters to the right of the equilibrium position and released, Determine A, the period of vibration of the system, B, the magnitude of the mass, B, the magnitude of the maximum velocity of bar AB. Yeah, so we need to find the period and the Vmax, our max velocity. So our so we've got our K constants on both sides, so the springs are equal. We have our point A and point B, so our bar AB, and then I just called the uniform cylinder C, even though I know that's the center point, but I just called it C just for saving lead, I guess, in time. So we have our mass of C is equal to 6 mass of cylinder is equal to 6 kilograms, our mass of AB is equal to 4 kilograms. The K constant is 5 kilonewtons per meter, and the X distance that is pulled is 12 millimeters, which we're just going to put that, so right off the bat we're just going to put that as 0.012 meters, just so that we can have all of our math right. We need to find the tau, the period, and our Vmax AB. So we have position 1 and position 2. Position 1 is with x equals 0.012 meters, velocity equals 0. Position 2, x equals 0 because it's in the middle, and our velocity max is still going in the left direction, and it is at Vmax right there. So T1, so our kinetic energy 1 plus potential energy 1 equals kinetic energy 2 plus potential energy 2. We have, so kinetic energy in position 1 is 0 because it is, because if it's being released, then you're not moving, you're holding it, and if it is just on one side of if it's vibrating back and forth, the acceleration is going in the opposite direction, but the velocity is at a standstill. It just pauses the velocity for a second. So our kinetic energy is 0. Our potential energy is 1 over 2 kx squared, and since both of the springs, spring 1 and spring 2, are both being stretched out, we're going to take this potential energy and multiply it by 2 because there's 2 of these potential elastic energies. Our velocity of our kinetic energy in position 2 is 1 over 2 mv squared, and remember this, and we got to remember that this is the mass of AB. This is the mass of AB because the velocity of C might be the velocity of C. I'm going to have to go back and rework the numbers because the numbers worked out kind of weird. But anyway, what I did is I put it as the mass of AB. It's probably the mass of AB and C. We're going to roll with it for now. Velocity squared plus 1 over 2 inertia omega squared, because we have the kinetic energy of the system, which is the cylinder and the bar AB, plus the kinetic energy of the wheel that's spinning, which is 1 over 2 inertia angular velocity squared plus 0. So plus the so the 0 is the potential elastic energy because the springs aren't moving. The springs aren't moving or they are moving, but they're not stretched. They're completely relaxed in position 2, and then as it's going this way, it'll compress. But position 2 is just here in the middle. So we move down. We can cancel out a bunch of we cancel out the halves out of the equation. We can cancel the halves out of the equation. We can cancel the r's on the right, the r squares on the right side of the equation, because our inertia equals 1 over 2 mr squared, because it's a cylinder, a uniform cylinder, and the angular velocity is our velocity over our radius. Our velocity is our Vmax, and our Vmax, and our radius is just the radius of the circle. These two cancel out, which shows us that this equation isn't dependent on the radius. And then we end up with 2kx squared equals mv squared plus 1 over 2 mcv squared. The only variable, all of the variables have a constant attached to them. K, X, MAB, and MC. The only thing that is the only one that we have is V, and that's the one we're looking for. And I ended up doing it out of order, so I got the B answer for the velocity max first. Anyway, so we'll do a bunch of reorganization, get our velocity on one side, input all of our numbers, and then we have a V max. V max of AB is equal to 0.0143, and yeah, because the velocity of AB, that's not actually correct, because it's just the velocity of the actual system, and you can't have a different velocity if they're attached at a point. So we're just going to call it the Vmax, because that's the Vmax of the system of the cylinder and of the bar. So we're going to move up to our period. We got our other equation. Our period is equal to 2 pi over our natural angular velocity. The x dot max is equal to our natural angular velocity times our x max, and so then we have V max equals omega n times x max. So we're going to input in our numbers. Our V max is equal to 0.0143 meters per second, equals to our natural angular velocity times our x max, which is our 0.012 meters. So then we'll do the equations, plug it into our natural plug it into our amplitude, which comes out to be 5.26 seconds. And this is why this number and also the Vmax, it is a really small system, and it's a heavy block, but I'm thinking that I might have done the ABC wrong, so I might rework those numbers and see what happens there. Anyway, here's my answer for question number 4.